Good morning, all of you. Today we'll start a new concept of this same chapter, dual nature of radiation and matter. Today we are going to discuss about what is De-broglie hypothesis, and we'll discuss also diffusion and Germer experiment. Okay, so basically previously we have studied that light has particle nature. Also in the previous chapter we have studied that light has wave nature. That means some concepts are there which can only be explained if we say light has wave nature. So for example, if I say interference, diffraction, this type of phenomena can be explained by light's wave nature. We also studied in this chapter the photoelectric effect. The photoelectric effect can only be explained if we consider light has particle nature, right? That means light has particle nature as well as light has wave nature. So I can say light have both the natures. Here light which we are considering as wave, now we are considering it as particle. Okay, that means we are considering that wave, light wave, or I can say radiation wave is behaving like a particle. So radiation, or I can say wave, is behaving like a particle here. So from this argument, from this statement, De-broglie, some state De-broglie, some pronounce it as De-broglie, some pronounce it as De-broglie. I will say De-broglie. Okay, De-broglie says that nature loves symmetry. His basic concept is nature loves symmetry. Nature loves symmetry. What that means? It means that if suppose I will say a tree is there, right? From a tree I get fruit, right? From tree I get fruit. It is a natural thing. It is the bliss of nature that tree is giving me fruit. At the same time, from the fruit, tree is taking birth, right? From the seed that lie inside the fruit, from the seed again tree forms. That means from tree we get fruit, again from fruit we get tree. That means it is a symmetrical process, it is a reverse process, it is in nature. So from this phenomena, De-broglie wants to state that as nature loves symmetry, so if wave is showing particle nature, so reverse is possible. That means particle will also show wave nature. It is the argument of De-broglie. So it is called the De-broglie hypothesis. It is called De-broglie hypothesis. According to De-broglie, as nature loves symmetry, and if wave is showing particle nature, so particle will also show the same wave nature. Particle will show wave nature. That means in every material that we see, it may be ball, it may be man, it may be tree, every particle in this nature have some wave property, right? So if particle has wave nature, it must have some wavelength, because the property of wave is it has wavelength. It has to whom we can say wave. Wave has which type of nature? Wave have wavelength, frequency, right? Wave have these natures, and particle has, to whom I can say particle. I can say one object as particle if it has momentum. Momentum is the property of particle. Wavelength and frequency are the property of wave, right? So momentum is the part. जिसके पास momentum है उसको हम particle बोलते हैं, जिसके पास wavelength है, frequency है, उसको हम wave बोलते हैं. चलिए, तो अगर हम बोल रहे हैं here De-broglie try to state that particle also have wave nature. That means particle must have wavelength. Particle must have wavelength. If particle have wavelength, then what is the value of that wavelength? So De-broglie calculated that wavelength. We have previously also calculated that P equal to S by lambda. In the previous class we have calculated this P equal to S by lambda. That means lambda equal to P by S by P, where what is lambda? Lambda equal to wavelength of particle, wavelength of a particle, wavelength of particle. Next, what is P? Momentum of particle, momentum of particle. And what is h? We know h is, what is this h? Planck's constant. Planck's constant. Its value is 6.63 into 10 to the power minus 34, right? Okay. This is the thing. Okay. Now, I am saying that particle have wave nature. Is it really real thing or just an imaginary thing? Let's try this. Suppose I'll say a tennis ball is there. Okay. We'll calculate the wavelength of a tennis ball. Suppose a tennis ball is there which mass is, suppose mass is 150 gram. Okay. Particle, it is a ball is a particle. Particle means it has some momentum, right? Momentum means it must have some velocity. So let us consider that velocity is suppose 30 meter per second. Okay. Suppose the mass of the particle is 150 and its velocity is 30 meter per second. Okay. So what will be the momentum? P. We know the formula, momentum P equal to mass into velocity. That is 150 gram. That means 150 into 10 to the minus 3 kg. Right? This into velocity. Velocity is 30 meter per second. So answer will be 45 into 10 to the power minus 1. That means 4.5 kg meter per second. That will be the momentum value. This is my momentum P. So this, if this is P, we have to calculate the wavelength. We have to calculate the wavelength. So let's write the wavelength formula. Wavelength lambda equal to h by p. H by p. So let's put the value of h is equal to 6.63 into 10 to the power minus 34. 10 to the minus 34, and p equal to 4.5 into 10 to the power, in 4.5. So if we calculate, the range will be nearly 1.47 into 10 to the power minus 34 meter. Wavelength unit is meter, right? So look at the range, minus 34, 10 to the power minus 34. That means the wavelength is very small. That means the ball which is having mass this and whose velocity is 30 meter per second, it has wavelength, but that wavelength is very small. It can't be visible actually. Okay, the wavelength can't be visible, so we cannot see the wavelength of the ball. Though I can, according to De-broglie, ball has some wavelength, but I cannot see the wavelength. I cannot see. Suppose I can see the waves in the sea. I can see the waves in the river, but I cannot see the wavelength of the ball here. Why? Because its wavelength range is very small. Okay. Right. So wavelength is very small here. Here I can say as lambda equal to h by p. That means if p is more, lambda will be very less. It is inversely proportional. That means if p is more, lambda will be very small. P is more means if mass will be very large, then lambda will be very small. Means for heavy particles, large particles, we cannot see the wavelength actually. Okay, for ball, या फिर man, tree, okay, these particles we cannot see the wavelength, we cannot measure, we can calculate the wavelength but we cannot see the wavelength, because for those particles the wavelength range will be very small. So we can see the wavelengths for small particles like electrons, protons, right? For those particles we can calculate and see the wavelength. This is all your De-broglie hypothesis. According to De-broglie, particle also have wavelength. Particle also shows wave nature. This is your De-broglie hypothesis.